In this chapter, we deal with the task of mirroring and reflection. And we start with the task of that we're given a point Q and a plane P, and we want to mirror this point at the plane. This is actually the basic task in this whole chapter. We will need it for all the rest of the reflections as well. Mirroring the point Q at this plane P means find the point Q dash on the other side of P such that it lies on the normal line to P through the point Q and has the same distance from the plane as Q. In other words, the vector QF vector equals to the vector FQ dash vector, or we can also say QQ dash vector is double the QF vector. Let us start by finding the point F where the normal through the point Q intersects with the plane P, so we have to intersect that normal with the plane. So let us find the equation of this normal line. Its position vector is the position vector of the point Q since it passes through the point Q, and its direction vector is the normal vector of the plane P, so 2, 2 minus 1. Intersecting the normal line with the plane P, we get this expression, so we get in the end 36 plus 9t equals 0, and hence t equals minus 4. Let me mark this point here with a star, so I can refer to it later. We find the coordinates of the point F by inserting t equals minus 4 into the equation here, and we find in the end F is 3 minus 4, 1. And so we get the vector QF vector as the difference between F and Q. And now using the fact that the QF vector is the same like the FQ dash vector, we get the position vector of Q dash the following way. Sorry, I miscalculated here the x component, it's corrected now. And we see we get in the end Q dash point is minus 5, minus 12, 5. An alternative way to find the coordinates of Q dash is to use the fact that Q dash vector is just double QF vector. And we get this relationship. We can use now this alternative to get an even simpler solution where we don't have to calculate at all the coordinates of the point F, namely just starting here. Since t is minus 4, then minus 4 times 2 to minus 1 is just the QF vector. So all that we have to do is we have to take 2 times minus 4 times this normal vector. Insert that into the equation of the line, and we get the position vector of Q dash. If this idea is clear to you, you can use it, and otherwise just use what we did before, find the coordinates of F, and by that find then the coordinates of Q dash. In example 2, we're given a ray of light L through 2 points through which it passes, Q1 and Q2. This ray of light gets then reflected at the plane P and continues as ray L dash, and it hits then a second plane P2, and we want to know where it hits that plane in what point. To find the equation of the reflected ray of light L dash, we need just 2 points of it. One point is the intersection point S of the original ray of light and the plane, and the second point we get by just mirroring any point on L at the plane P. In this case, we'll just take the point Q1 and we'll find Q1 dash, and then L dash is just the line passing through Q1 dash and S. Let us start by finding the equation of the line L, which passes through points Q1 and Q2. Oh, there are 2 mistakes in the task. The point Q2 is 8 minus 1 minus 1, and the plane P2 has the equation x minus 1 plus 2z minus 7 equals 0. Well, using this, we get now the equation for the line L, which should be self-explanatory, and we can now find the intersection point between L and P, which is then the point S. And we get 36 minus 18t equals 0, and hence t equals 2. And we obtain the coordinates of S by inserting the value 2 for t in the equation of the line, and we get S is 5 minus 6, 1. Next, we need to find the point Q1 dash, which is the point Q1 mirrored at the plane P. So we can use exactly what we learned in example 1. And by the way, it's exactly the same task, even with the same numbers. Nevertheless, you can practice it. I'll write it down as well. Maybe you want to stop the film. And so we find the mirrored point Q1 dash as minus 5 minus 12, 5. The equation of the reflected ray of light corresponds to the equation of the line through the points Q1 dash and S, and hence we get please note that we could have used for the position vector also OQ1 vector, but it makes sense to use the point S, since the point S is really part of the reflected ray of light, while the point Q1 dash is only an artificial point, since the beam of light will go like this. This equation is just, we have simplified the direction vector to have the most simple possible one. The last step is to find the point where this reflected ray of light hits the plane P2. So we have to intersect L' with P2. And we get this equation here, and hence t equals 3. And so the point R is 23 minus 5. In example 3, we have again a ray of light that passes through a given point. It gets reflected at a given plane, and then it passes through a given point again. The task is to find the point of reflection S and the equation of the reflected ray of light L'. Here you see a sketch of the situation. Since only the points Q1 and Q2 and the plane are given, the question is how can we solve the task? Well, the idea is rather simple. We just need to reflect the point Q1 at the plane P, and then from here through Q2 we get the line L'. So the first task is to find the point Q1 dash, a task that we have now done several times. Try it on your own, stop the film, and then verify and continue. And we find Q1 dash as coordinate 6 minus 11, 3. Now we can find the equation of the reflected ray of light as the equation of the line Q1 dash Q2. And we get this equation for L'. The last task is to find the point of reflection S, which means that we have to intersect L' with the plane P. And we get the equation minus 120 minus 21t equals 6, so t equals minus 6, and so we find the point of reflection S is 2 minus 1, 5. In example 4, we have again a light beam that gets reflected at a plane. We are given a point Q on the original light beam, a point R on the reflected light beam, and a point S where the light beam gets reflected. And the task consists in finding the equation of the reflection plane P. The idea how to find this plane is the following. The normal line through the point of reflection S, normal to the plane P, is the angle bisector of the line L and the line L'. So this means we have to find the angle bisector of L and L', and namely the correct one, so the one here, not the one here. And then by having that one, we can simply find the equation of the plane. So what we need are the unit direction vectors of L and L' in the shown directions. The direction vector of the line L is the SQ vector, and hence the unit direction vector is the direction vector divided by its length, so 1/3 times the direction vector. We do the same for the reflected light beam. So SR vector is the direction vector of the reflected light beam, 148, and since its length is 9, we get for the unit direction vector 1/9 times 148. To simplify the calculations afterwards, we expand this unit vector to 1/9. And we find for the normal vector the sum of the two unit vectors, and we get in the end 1/9 times 7, 10, 11. And hence we find the equation of the plane 7x plus 10y plus 11z plus d equals 0. And we just need to insert a point S to find d. And we get the final result for the plane P, 7x plus 10y plus 11z minus 43 equals 0.